we have reciprocal functions to talk about today. Why looking at this one, it's called a reciprocal function. What makes you think reciprocal with that? So when you have a reciprocal in a fraction, it means what? What do you do to find a reciprocal?
Flip it.
You flip it. So it is kind of like a flipped over thing. A reciprocal function, it's also an inverse relation. You remember the inverse relations, y equals k over x? So this particular textbook calls it a reciprocal function. When we go over it in physics, I refer to it as an inverse relation because it really is. It's the same thing. So reciprocal function like that. So what we're going to do is we're going to graph this thing. So what I need for you guys to do, we're going to start to make a chart. I want you to be able to identify some things that are happening with this graph. All right, so drawing your x and y axis. What we need to do then is we need to figure out the x and y values. We're going to start with the positive side, and we're going to pick some values for x. So when x is 1, you divide 4 by 1 and you get 4. And you go ahead and graph that point. When x is 2, we do 4 divided by 2, and that gives you 2. And we graph that point, 2, 2. When x is 4, we do 4 divided by 1, 4 divided by 4, and we get 1. And then you go ahead and you graph that point. Then what we can do is we can think about maybe some numbers down the line just a little bit. If we were to plug in possibly a half, 4 divided by a half actually turns out to be 8. What we notice is that the products always come out to be the same number. These products are always 4. So we can graph the ordered pair 1/2, 8. But keep in mind that also if you switch those around and you put 8 first, the ordered pair 8 1/2 would also make sense. If you plug in 8 for x, you get 4 divided by 8, which is 1/2. Once again, the product turns out to be 4. So we graph that point, and then we get a good representation of what the shape of the positive side of the graph looks like. Then what you need to do is you also need to take a look at the negative side of the graph. So you begin to plug in the negatives that go right with the positives. -1, 4 divided by -1 is -4. And you go ahead and graph that one. -2 gives us -2. Notice that the numbers are just the same as the numbers on the positive side. It's just that now they're the negative ones. Same thing with the little half numbers. -1/2 would give us -8. -8 would give us 1/2, -1/2. And you graph that, and we find out that every reciprocal function is going to have the same basic shape. You're going to have a one piece, and then you're going to have a pair of lines that are going to divide it up so that you've got a curve on one side and a curve on the other side. The other thing that we can keep in mind is that every graph has those two lines that divide it up are called asymptotes. You have a vertical and a horizontal asymptote. These are the lines that the curves are approaching, but they never cross over. Now, the other thing that we can consider is that the asymptotes tell us the values that x and y are not allowed to be. So x can be anything in the whole universe except for it can't be 0. We all remember that it can't be 0 because you divide by 0 and you get a false answer. So our domain value is when x does not equal 0. The range is when y does not equal 0. And our asymptotes are those lines that divide it up. So on your paper we have an example of showing what happens when we begin to stretch and we begin to compress, or in this case when we do these type of functions we call it shrink, the various different parent functions. If you'll notice the graph there that's done in black is the 1 over x graph, but when you take a equals 6, in other words we put a 6 over top and we do 6 over x, we get the idea of a stretch, and it stretched it away from where the black graph was and it brought it up to where that red graph is. Okay, notice that it just takes it a little bit further away from the asymptotes, but it does keep it with having the same asymptotes. When you have a number that is smaller than 1, or their absolute value is smaller than 1, we end up having a situation where the graph shrinks, what they call it shrinks, and it gets closer to the asymptotes, but it still does not cross over the asymptotes. With the negative, it becomes a reflection. Notice the green graph is really a reflection of what's going on with the red graph. Okay, so the negative makes it a reflection. It matches most closely with the a equals 6 graph, so it's also it's a stretch and it's a reflection. Now, most of what we're going to focus on is the moving left, right, up, down, but I do want you to notice that, those stretches and those shrinks still do actually happen even in these particular types of graphs. Now on your paper also we have the rules for them. They haven't really changed from the rules that we've used for all of the translating of the parent functions. If the number is bigger than 1, it stretches. If it's less than 1, it shrinks. Negative reflects. Same as what we've been dealing with before. If you look down where the x is, the one that's grouped with the x tells you whether it goes left or right with the same rules we've been using. And the place with the thing that comes on the outside, k, it will tell you up or down. Now think about for a minute why x can't be h. We can look into the denominator, and if x was equal to h, you'd have h minus h, which would equal 0, and you just can't have a 0 in the denominator. So what we want to do next is take a look and describe the translation that goes with this, and then after we do that description, we're going to go ahead and graph it. So think about the 3. The 3 will mean that you have a stretch. The 1, the plus 1, means that it will go to the left 1, and the minus 4 will mean that it goes down 4. All right, think through, I want you to think through the next one, okay? And what does the 1 do? What does the negative 3 do? And what does that 2 do for you? And hopefully you did remember that the 3 would move it right 3 and then up 2. Then we're going to work on taking a look at the process to graph these things. What the easiest thing is for these type of translations is to identify the asymptotes. And once you identify the asymptotes, we're going to be able to very easily get the general shape of that inverse or reciprocal function. So we find those by looking at the directions telling you whether to go left or right or up or down. And on our graph, you think about when you move left or right, that's an x-axis type of thing. So that means that left 1 means that x equals negative 1 is an asymptote. X can't be negative 1. Down 4 means that y is going to equal -4. That will bring the whole thing down 4 units. When you have the situation for right 3, that's where x is going to equal a regular positive 3. And when you have up 2, that means that we're going to have y equaling 2. You always look at, ask yourself what did it do, and then you can easily find the asymptotes. Now, as far as graphing goes, once you know what the asymptotes are, you actually just go ahead and easiest thing to do is actually graph it as a point. Like x is -1, go -1, -4, and graph that point. Then the asymptotes are just the lines that go horizontally and vertically through that point. And that makes it very easy to sketch in the asymptotes. Notice that we're going to do this with a dashed line. We do this with a dashed line because the asymptotes are not really numbers on the graph, but the asymptotes just help us to give form to our graph. So we put in our asymptotes, and then what I'm looking for you to do is to just do a rough sketch of the graph, knowing that you've got one piece up there, and you've got the other piece down there. There will always be a positive and a negative side for it. Remember, with asymptotes, it cannot cross over the asymptotes, and it makes it a very nice way to be able to make a graph if you've got that framework as far as where it starts. Now, what we're going to do is we're going to take a look at another one, and I want you to take that one below it, the y equals 1 over x minus 3 plus 2, and I want you to sketch in those asymptotes for yourself and do that graph. All right, so now that you've done that, you can kind of, this part really is in your notes already. The colors make it a little bit more obvious where the asymptotes are. You don't have to do it that way. It just makes it a little bit easier to follow. Once again, once you put in the asymptotes, I'm just looking for you to do the general graph of that. All right, so we have another one fresh to work through. It will be good for you to be able to describe a graph, find the asymptotes, then use those asymptotes to sketch the graph, and then from there state the domain and the range. So first of all, describing the graph. What we can do here is look at the different pieces. The 2 tells us that we're going to stretch. The 2 tells us that we're going to stretch 2. The 1 tells us we're going to go right 1. And the 3 tells us that we're going to go down 3. As far as the asymptotes go, remember that the asymptotes come directly from our instructions to whether we're going to move right or down. So right 1 tells us that we have an asymptote at x equals 1. And down 3 tells us that we have an asymptote at y equals 3, -3. So when we sketch the graph, we're going to use the idea of x being 1 and y equal -3. Easiest thing to do is to think about moving right 1, down 3, placing that point, and drawing your asymptotes through that point. So we will move right 1. We're going to go down 3, place the point, draw in your asymptotes. Remember, they're not actually part of the graph, so we need to make that into a dashed line rather than a regular line. And that's one confusion that a lot of people have, is thinking that the dashed line, the asymptotes are actually part of a graph. They're not actually points on the graph. They're actually just places where you can't have any points. They're like no point zones. So you can then just sketch in the graphing part of it. And so those curves there are actually the graph. Now remember, the domain is what the x and y are not allowed to be. So we say that x can be anything, but x is not allowed to be on the asymptote. X is not allowed to be 1. So we'd say x does not equal 1. And with the range, it's what values is y not allowed to be. Y can be anything, but once again, y is not allowed to equal -3. That's our asymptote, and that's the whole point to having the asymptotes. So once again, going through the process, describe the graph, find the asymptotes, sketch them in, determine the domain and the range from the information that you already have. Now, in the writing of an equation for a translation, you take the parent function and then use the things you know about up, down, left, right, and the asymptotes to be able to write a new equation. So our new equation here is y equals 3 over x plus 2 plus 5. Now it's plus 2 instead of minus 2, because if you plugged in a minus 2, you'd get a 0 in the denominator, and remember the asymptotes show where you're not allowed to have points. So x plus 2, and then the plus 5 moves the thing up 5 units. So you take a look at the numbers and you figure out what needs to go where on those. Let's try another one. Okay, take a minute. I want you to take a look at this one and see what you can figure out. Think about, what does the 3 tell you? What does the -4 tell you as far as where this graph is supposed to move? In thinking this one through, you should get that y equals 3 over x minus 3 minus 4. So that brings it to the right 3 and it brings it down 4. Sometimes before you can begin to solve and graph, you have to solve for y first and use the algebra that you already know. You know the process of going ahead and adding 3 to both sides, so that xy ends up equaling 8, dividing by x, and then ultimately getting y equals 8 over x. And we can, when we start to graph this, it doesn't move up, down, left, or right, but we can be a little bit more exact in our points. You know, thinking through our graph with our x and y axis. If you recall from what we did before, you may have noticed that the product of x and y always turn out to be the same number. So in this one, we're looking for the product of the two numbers to come out to equal 8. So when x equals 1, y is going to actually equal 8, so we have the ordered pair 1, 8. When x equals 2, 8 divided by 2 is 4. And when x equals 4, we get a 2. And then finally, when x equals 8, 8 times 1 equals 8. So once again, 8 divided by 1 also is 8. So the ordered pair 8, 1 would be our last point on the positive side, just to get the shape. Of course, there are many other points available to graph, but we're looking for just a few key points to make a nice graph approaching those asymptotes. And then on the other side of things, we also have the negative counterparts. We have -1, -8. We have -2, -4. And we have -4, -2, and then of course -8, -1. And that gives us our nice graph of our inverse function. And with that, we have come to the end, and that's a much nicer graph with a little bit more care taken. And that's it. Have a very blessed day.